the average versus the instantaneous. Average being the slope between 2 points on a curve, right? Average rate of change we talked about before. Average velocity, just where, how long did it take to get from here to here? And if you look at the y values, how far did you go? How far did you go? How long did it take? That's what your average velocity is. The derivative of the position function at a single point here is the velocity of the thing at that given point. It can change, right? Calculus lets you find the speed or the velocity at any point along there, even if it's dynamic and changing. The words speed and velocity often get used interchangeably, but when you talk about, in physics they say one's a vector, one's a scalar, or one you don't care about the direction and one you do. In mathematical terms, you can say that speed is the absolute value of velocity. The absolute value of a number, you learned this kind of thing before, right? The absolute value just says how far from zero is it, basically, and I don't care whether you're going that way or that way. The absolute value of 3 is 3. The absolute value of negative 3 is 3. It's just saying how far from zero is it. What's the number part? What's the actual number, not the direction, right? Not whether it's positive or negative. So the speed is absolute value of velocity. You ignore whether it's positive or negative. You have a speed limit. You don't have a velocity limit, right? If you had a velocity limit of 100 kilometers an hour, then going backwards at 200 kilometers an hour would be okay, right? But officer, I was going the other direction. Acceleration. Acceleration, you probably know from kind of your work in physics and maybe other science courses. Acceleration is the rate of change of what? Velocity. So it's actually the second derivative of the distance function. Second derivative. Or the first derivative of the velocity function. Right? So symbolically, that's what it says there. Acceleration you could write two ways, right? Well, a of t it's either v prime of t or it's s double prime if you're using s, like they do in the textbook. Second derivative, right? Like what we were looking at with those physics formulas up here. If you start with your projectile formula, the first derivative gives you the velocity, whatever the initial velocity is, plus how much it's changed, right? Think about what those formulas mean. You might not have ever thought about it before, but if you, when you're talking about the position of something, it's affected by three things, like we said, right? Those three different terms, each one affects how high this goes. So if I throw this ball in the air, three things are going to affect how high it goes, assuming we're not looking at air resistance or any of those kind of things. How high I throw it from, what initial velocity I give it, and then the effect of gravity. On Earth, this is fairly constant. It's not actually perfectly constant. It depends on different things if you go to different altitudes and stuff, but more or less at sea level, gravity is a certain number that you know. If you throw this ball up in the air, again, if I throw it from down here or throw it up here, that makes a difference. If I throw it with more velocity, it makes a difference, and then gravity changes it. If you think about the speed of the thing at any given time, it's whatever I give it at the beginning, and I'm saying speed, I should be saying velocity, right? So if I give it, I don't know what number, what meters per second I gave it, but some kind of initial speed, and the only thing changing that, if there was no gravity and I threw it up like that, it would just keep going, right? If there was no gravity, this wouldn't be there, and all that would happen is it would just keep going with that same velocity. When you have an acceleration of, if position is in meters, and this is in meters per second, anytime you take the derivative, it's turning it into a rate, right? If you start with meters, the next thing, first derivative is going to be meters per second, and then you get meters per second squared. And if you took the third derivative, what would you get? Not that you've probably talked about the third derivative before, but what would you get if you did do the third derivative, if you differentiated it again? Yeah, rate of change of acceleration would be, I'm not sure how well you understand what this meters per second squared means. It means meters per second, but you don't write it like that. It's how many meters per second is it changing every second. Just like this is saying meters per second says how many meters is your position changing every second. This is saying how many meters per second is it changing every second. Well, if the acceleration due to gravity is negative 9.8 meters per second, it's changing every second. This is, well, it's losing approximately 10, right? It's losing approximately 10 meters per second every second. 9.8, approximately 10. So if I could throw, if I fired this thing upward at 100 meters per second, after 1 second it would be going approximately 90, right? Like it's losing that much every time. It's dropping by that much every time. That's all that this formula is saying is, well, it's losing 10. It's a linear function, right? Negative, I'm going to put 10 just so we can think about it a little easier here, right? Roughly negative 10t plus whatever I give it. So I've started at 100. All that means is every second you add, you're losing 10 more. That's what that means. Negative 9.8 meters per second squared just means every second you're losing approximately that much. If you did the next one, it would be meters per second cubed, or it would be meters per second squared per second. How much acceleration are you losing? In this case, what would the third derivative be here? If this is a constant, what would the third derivative be? It's going to be 0. It actually has a name. What do you think the name of the third derivative is? It's later on in this thing, but it's called the jerk. What? You don't believe me, do you? I did not make that up. It's in my handout. It must be true. No, it's called the jerk because I guess it comes from sudden changes in acceleration are kind of like jerky movements. Like if you suddenly change the acceleration of something, the way they describe it in the textbook is good. They say acceleration isn't what spills your coffee cup in the car when you're driving. Different accelerations aren't what kind of spills the coffee cup over. Changes in acceleration are. Or in other words, if the jerk is not 0, if the jerk is something else, that's changes in acceleration. You can get in your car and hit the accelerator, and your position graph's going to look like that. Some kind of constant acceleration. Your speed's changing, constant acceleration. If you were to do that, though, and you suddenly hit a tree, then you're like this, right? That's where this suddenly changed. Or sorry, that's where your acceleration suddenly changed, right? Velocity was increasing, then it was different. That's where your coffee goes flying forward, and that's where everything in the back of your car comes flying forward and hits you in the head, right? If you're packing your car, don't put stuff loose in the back seat that's heavy, certainly, because if you suddenly change your acceleration, it's going to hit you. That's later on, that third derivative. If you had a situation that we're not necessarily familiar with, where this was the third power here, like if this is cubed or something like that, then we'd have this where it's not equal to 0, right? You'd have some acceleration that's not just a constant. Anyways, we're off of a bit of what we were looking at, but the second page here, just some making sure we know what's happening with each of these things, right? We said if S of t represents distance or position, depending on what you're looking at, right? The reason sometimes better to call it position is because if it becomes negative, like it might make more sense to say you're behind the starting point or in front of the starting point, but we can kind of use those interchangeably. This is velocity. This is acceleration. If you want to add the third derivative there, it's called jerk. It's later on in the handout. It's noted there, but that is the derivative of acceleration. Changes in acceleration. Acceleration is rate of change of velocity. Velocity is rate of change of position, right? The derivative is the rate of change of something else.